This is the first tutorial for chapter Electromagnetism. I know, long word, new topic. It's a bit tricky, especially in the later parts, but that's why we've designed these tutorials. We hope that we can help you with these. So I'm going to start off. This is one of the tricky chapters, but the first part is not really that tricky. You you should be able to get it, if not the first go, the second go at least. If you don't, then you can look at this tutorial here. So, electromagnetism, the whole chapter is about how the two words over here, electro and magnetism, are very closely linked. By electro, we're referring to electrical energy, electricity, and magnetism, of course, you all know. I think last year you had a chapter on it as well. So you know the properties of magnetism. So it's all about how electricity causes magnetism, how magnetism causes electricity, and a lot of other stuff. And on the face of it, it looks like a tough chapter. But if you get into it, it's very interesting, and it forms the base of whatever's around us. All your motors, all your generators, everything that runs on electricity at your home, even the computer that you're watching this on right now, the TV, it's all there thanks to your generators and motors. So electromagnetism, the basic idea came into being in the 1800s when there were experiments carried out. You had a circuit. I'm not going to draw each part of it, but you had a circuit. So this is positive, negative here. When you switched on the current, and say you placed a compass over here, what you saw was a small deflection. Direction of deflection, I will come to that later because I need to teach you something else for you to determine that. And also other properties like if you reverse the direction of the current, if you have it this way instead of, if you have it clockwise instead of anti-clockwise, the direction of the compass will also change. And also that if you place the compass below the wire, again it will reverse. So there were properties like these which were observed, and this is the explanation was all given using the hypothesis that a current carrying wire, which is our orange wire over here, produces a magnetic field around it. That was the first theory put forward. That's simple enough. You don't go into where's the north pointing to, which way is it going. Just listen for now, and I'll come back to this later. I'll leave it over here for now. And then there were more experiments done on the magnetic field caused due to a straight conductor, a straight wire. So say you have a straight wire like this. There's a nice diagram given in your books where you have a piece of cardboard over here, and there's the experiment carried out where you put pieces of uh, iron filings on the cardboard, and you'll see them get arranged. So here is your circuit. Say this is plus or minus, it doesn't really matter over here. So what you see is that around this wire that pierces through the cardboard, you see the iron filings arranging themselves in the direction of the magnetic field. Not in the direction of the magnetic field, but definitely in the shape of the magnetic fields around the wire that are produced. Again, I'm not going into direction right now. I need to tell you something else for you to determine the direction. So again, I'm leaving it here. These experiments were carried out. Also, iron filings arrange themselves in such a way because of the magnetic effect. Because the magnetic field was produced, they were attracted towards the magnetic field. Iron is a magnetic substance. So now, of course, you had more layers like this, but I'll come back to this again. Now, you have something called the right hand thumb rule. In this chapter, you're going to have three main rules. One is the right hand thumb rule, one is your Fleming's left hand rule, and your last is your Fleming's right hand rule. please don't get confused between the three. If you mess them up, then a lot is going to go wrong. So the first most basic one, which we use over here in this part of chapter, is called the right hand thumb rule. So I'm sure if you read the text, you see what it is. This is a conductor. I can't draw a hand here, but say you're holding on this wire. Just imagine. So the direction in which your thumb points will be, say, it'll be like this or it'll be like this. Just point it in the direction of the current. If the current is like this, then point your thumb like that, hold it like that. Or if it's going down, then do it like this. And you'll see that your fingers curl around the wire in the direction of the magnetic field. So just imagine you're holding the wire with your thumb pointing upwards. You'll see your lines come like this. And the opposite will be true if you have your thumb pointing downwards. I'm sorry, that's the other way. This will be the direction. Then be clockwise. So that's basically the right hand thumb rule. So if you know the direction of current and you have the wire in your hand, you can just imagine you're holding it. You can tell the direction of the field lines. So say over here in this example, the current is like this. Imagine you're holding this part of the wire here. The thumb will be pointing downwards. So you can say that the magnetic field will be something like this. It'll go in this direction clockwise. If I give you the opposite, if the current is going like this, then your thumb will be pointing upwards when you're holding that wire, and so it'll be like this. It's that easy. And the same thing actually can be applied over here in the first example. If your current is going in the clockwise direction like I've drawn here, and just imagine that you're holding this wire here. So your thumb will be pointing towards the left hand side, and your fingers will curl just around this. I don't know how to represent it, but it'll be something like this. And so you can see the deflection then. I think a better explanation in your textbook. I can't really explain like this, but all I can tell you is just apply the right hand thumb rule and you see it all fits in perfectly over there. So you can, the 5 different cases you can see for all of them. Then next we come to, here we did straight conductor. Now if we do the same thing for a loop, we're going to see, again we have a cardboard over here. Cardboard is here. I know the drawing is not very nice, but over here say the current is going like this. Just take the sides as straight conductors and apply the right hand thumb rule, and you'll see that again there are iron filings here, so they'll get arranged like this in a circular pattern, concentric circles, and the direction you can easily determine by the right hand thumb rule. So if you're taking this example here, your direction would be like this. And take the second wire now. These are your iron filings, and your direction will be this way. And you'll also see that when your iron filings that are near the center get arranged, they form nearly straight lines. And this whole pattern actually resembles the magnetic field lines of a bar magnet, which has lines going like this. You can read more about that in your textbook, or even in your last year's textbook, it'll be there. So then this was compared to a bar magnet, and so it was said that this whole loop can also have faces, like a bar magnet has faces like this, north and south, where your field lines go from north to south. The same way you can say that this face of the coil, if you're looking at it from the screen point of view, you're looking into the screen, you could say that if the current is going in the clockwise direction, which it is over here, you can see the arrows, then this face can be considered the south face. If it's going anti-clockwise, if you look at this from the other side, it'll be north. So just remember, clockwise is south, anti-clockwise is north, and this will come used later in the chapter as well. And this actually, when you talk about a solenoid, which is many coils together, it's something like this. So over here, it's not just one loop, but it's many loops. So again, if you just look at this from one side, say the current is going like this. Imagine that this is a loop. Imagine that you're standing somewhere here. If you look at it from your point of view, the current is actually going in the clockwise direction in this wire here. So this will be the south face for you. And if you look at it, another arrow here, if you stand over here, then this face for you will be going anti-clockwise. This will be the north. So this is how it is summed up, that a current carrying conductor, whether it's a loop or a coil, cylindrical coil, which is a solenoid, or anything like that, it acts like a magnet. It'll induce a magnetic field around it. And it's very similar to a bar magnet, but there are huge differences as well. Electromagnet, it's a strong magnet. You can vary its strength, but the main thing is that it is a temporary magnet. As long as you have current in this wire, the magnetic field around it will stay, and this whole system will be called an electromagnet. And you can easily increase the current, so you can increase the magnetic field, you can increase the number of turns, so you can manipulate it in such a way, and you can make it really strong. That's the main difference. You can even reverse the polarity if you like by just reversing the electrical current. So that's all that is in the first section. There's also you've been given the working of an electric bell, and I think if you got this so far, you can just figure out the working yourself, because there's not much to it. In your books, it's explained in a very detailed fashion. I don't think you should have any problems over here in electric bell. It's a simple mechanism. The electromagnet keeps turning on and off, on and off. So your hammer keeps going back and forth, and so it keeps hitting the gong again and again, which is why you hear the sound as a continuous sound. Of course, I'm not going to cover it now, but if you have any doubt over here, you can always contact us, we'll tell you. But I'm not going to do it over here. I don't think there's any need to, but you can go over this video again if you have any doubts. And I think that'll solve your doubts in the bells working as well. So that's it for this tutorial, and next tutorial we'll move on to the next section, which is definitely very important and covers the DC motor.